Hello and welcome to this screencast presentation given by Group 4. The title of our project is Localization Algorithms and Technologies. And what we basically did was to make a research about the state-of-the-art localization algorithms in wireless sensor networks and then use that knowledge to make our own implementation of such an application. So this is the agenda for this presentation. Initially, the motivation of our application, the specific application, and the application quality of service requirements will be explained. Up to this point, we set a clear goal regarding the application that we want to develop, which will be based on a wireless sensor network localization system. Then a survey about localization systems is introduced, where we will discuss which methodologies and algorithms exist and which one we will choose for our purpose. This will be followed by the implementation, where we will simulate the chosen localization system. Then some experiments will be done to check whether the system satisfies the quality of service requirements of the application. Then finally, the results and the conclusion from these results will be laid out, and in the end some future work will also be introduced. So then we start with the application motivation. We found some interesting information about India, where in the last years the train tracks were modified to allow the trains to run faster. Many of these trains run through protected areas, and this has caused a huge increase in animal death due to accidents. Out of the several animals affected, the worst part was for the elephants. Therefore, we propose an application which will track the elephants in large areas to collect data, which will then be used to draw density maps. This information can be used in two ways: to take into account when building new roads or train tracks, or to know which critical points to signal the already existing ones. So now we will introduce the quality of service requirements of our application. The position will be updated every 20 minutes for at least 95% of the nodes. The latency upper bound will be 1 minute for at least 95% of the nodes. The position in error will be at most 5 meters for at least 95% of the nodes. And then mobility is necessary, since these wireless sensor nodes will be attached to the elephants. So now that we know which application we want to build, so we do some research about the state-of-the-art localization algorithms to be able to tackle the problem. So every localization system can be divided into three parts: the distance or angle estimation, the position estimation, and the localization algorithm. There are a lot of different possibilities for each of them. Unluckily, there's not enough time to cover all of them in detail in this presentation, so I will only mention them and give a motivated explanation of the ones we chose. Then regarding distance or angle estimation, the possibilities are radio strength signal indicator, time of arrival, time difference of arrival, or angle of arrival. And there is a trade-off between computation and accuracy. Regarding position estimation, the possibilities are trilateration, bounding box, triangulation, or also some probabilistic approaches. And then again, we have a trade-off between computation and accuracy. Then regarding localization algorithms, there are a lot of different options, and a lot of different localization algorithms have been used for different purposes. Some of them are ad hoc positioning system, mobile positioning system, or recursive positioning system. As we see, there are many possible combinations, and it should be chosen based on the specific application and its quality of service requirements. We finally chose RPE algorithm, which stands for Recursive Position Estimation Algorithm, with RSSI and trilateration, because it seemed like the most efficient solution regarding cost and accuracy. RSSI is used to estimate the distance between two nodes based on the strength of the radio signal. It is the cheapest solution, and one possible drawback is that it may be affected by the environment. Then trilateration consists on estimating the position of a node with respect to other three nodes to which the distance is known. It shows a good compromise between complexity and accuracy. And this is the basics of the recursive position estimation algorithm. Initially, the green node is able to estimate its position with respect to the gray nodes, which know their position. Once it estimates its position, it will broadcast it, and other nodes can use it to estimate their positions. The position thus propagates through the network. The main advantage of this localization algorithm is that you can reduce the number of beacons, which are more energy consuming than normal nodes. The drawback of this implementation is that if you make an error in estimating the position of a node, this error will propagate through the network. So we will study how this affects our implementation in the simulation part.
Now we talk about the implementation of the application. We implement it on the Contiki system and simulate it on the Kuja simulator. The application has three types of nodes. Sync node, which collects the localization information, beacon nodes, which are reference nodes used to localize, and non-beacon nodes, which are mobile and needs to be localized. The application knows the positions of the sync and the beacon nodes beforehand. Implementation includes following steps. First, we estimate the distance between the nodes using received signal strength indicator. Then, using the above estimated distances of three already localized neighbors, we estimate the position using recursive position estimation. Finally, we implement a routing algorithm to gather all the localization data at the sync node. We will discuss each step in more detail in coming slides. The first step is to estimate the distance between any two nodes using received signal strength indicator. This is a hardware link quality estimator and is readily available in almost all wireless sensor nodes. To obtain a relation between RSSI and distance, we conducted an experiment with different distances between two nodes and corresponding RSSI values and plotted them. From the graph, we see that these two are linearly related and is given using this formula. Since a regular wireless sensor node is not advised to perform any floating point operations due to its high processing power requirements, the distance here is rounded to the nearest integer. In the next step, we use the previously obtained distance values and recursive position estimation technique to get the coordinates of the nodes. RPE uses trilateration technique. That is, when a node has three localized neighbors, it uses them and builds three equations and solves them for its own position. Since we have two unknowns and three equations, a solution is guaranteed. For more details on how these equations are solved, please refer to the report. Finally, all the positions of the localized nodes should be collected at the sync node. To understand this, let's first understand how the position propagation is done to localize all the nodes. Every non-beacon node once estimates its position using three reference neighbors and remembers them. These localized neighbors are used as reference nodes to their non-localized neighbors. Once all non-beacons are localized, to collect the data, a routing algorithm similar to the directed gossiping is used. The routing is directed towards the sync node, so the path reverse to the position propagation is used. Localized nodes send their positions to one of the three reference nodes they used for their position estimation. Finally, all this data reaches the three beacons which are in the transmission range to the sync node. At this penultimate stage, the three beacons send this data to the sync directly. To understand it more clearly, assume during position estimation the nodes only A, B, and C are localized. Node D to estimate its position uses A, B, and C. Once D estimates its position, it becomes a reference node to E. So the node E uses A, C, and D to localize. In this way, position estimation propagates. And during data collection, once D estimates its position, it sends its position information to either A, B, or C, and these nodes propagate this information back towards the sink node. Once this data is obtained at the sink, the data can be used further for various purposes such as to make animal density plot, to alert the drivers if the animals are very near to the road, and so on.
Now the experiments, we have set two goals. First, to study the system's scalability with nodes, and second, to study how increasing area affects the system for a fixed number of nodes. For this, 4 experiment setups are required. First with 25 NBs spread over 15 to 50 square meter. Second with 50 NBs spread over 15 to 50 square meter again. Third again with 50 NBs but spread over 75 into 75 square meter. And in the fourth setup, 50 NBs are spread over 100 into 100 square meter. Now let us look at the simulation steps. We start the simulation with 0 millisecond mode delay. Then we insert the sync node, 3 beacon nodes, and all the other non-beacon nodes. Note that position of sync and beacon nodes are fixed in the code. Now we load the positions.dat file using mobility tool. Note that this file contains positions for all the nodes. Now we start the simulation. This arranges the modes according to the dat file. Now we reload the simulation and wait for at least 15 milliseconds of simulation time. We save the log file and extract the data. This is a short video of the simulation. Let us have a look. Before discussing the simulation results, let us look at the parameters used. First is the error caused due to distance estimation and is calculated as mean squared error. That can be seen in the diagram on the right, where x, y is the estimated coordinate obtained from the experiments and x0, y0 is the actual coordinate of the mode. Second parameter used is latency. We have divided it into two types, position estimation and data collection. From the figure, if 3 beacon nodes start transmission at T1 to T23 and the non-beacon nodes estimates its position at T4, then the position estimation latency is defined as the difference between T4 and minimum of T1 to T23. Similarly, if the non-beacon node announces its position at T5 and the packet reaches the sink at T6, then the data estimation latency is the absolute difference between the timestamp T5 and T6. However, calculating latency using this approach suffers from synchronization problem. To maintain a common clock frequency, the mode clock needs to be synchronized globally. To do so, in the simulation, the mode startup delay is set to 0 milliseconds before starting a new simulation. For actual experiments, same techniques have to be implemented. The timestamps used for latency is clock time and the clock seconds. These are the APIs in the QJOB. Now the results. Results are divided into two scenarios. In scenario 1, the experiments are performed in a given area of 50 into 50 square meters with increasing number of modes. You can see from the top graph that distance estimation error decreases with increasing number of modes. It could be because error propagation and hence accumulation is less with increasing density. The bottom graph shows the percentage of modes that estimated its position wrong. Increasing density leads to more noise or interference and hence the behavior. This is the latency behavior for scenario 1. You can see that latency decreases with more modes. This is because as modes do not have to wait for other modes to estimate their position using the RPE algorithm explained before. However, data collection latency that is shown on the bottom graph seems to show an increasing behavior. This is because now more modes are trying to send the data to the sync node, leading to increased contention and waiting time. Now the results for scenario 2. In this scenario, we tried to simulate the decreasing density behavior by fixing the number of modes to 50 but distributing them across the increasing area. From the graph, we can see that distance estimation error increases as the nodes spread across a larger area. Since now the probability of nodes to be in the range of beacons or nodes which are closer to beacons decreases, error propagation is enhanced because of the use of RPE algorithm. The bottom graph shows that the percentage of modes which wrongly estimated their position significantly increased when the modes are distributed in a very large area of 100 into 100 square meter. This could be because of the wrong distance estimation using RSSI method, which is greatly affected by the path loss model. This is the latency behavior for scenario 2. As seen in the top graph, the latency behavior for position estimation seems to give a random behavior, and so nothing logical could be inferred from the data. It is advisable to have more simulations data for a better trend. However, the data collection latency shows a decreasing trend. This trend could be because of random modes distribution. Again, more extensive simulation data is required for consistency. Now, here are some final conclusions drawn from the results. The worst position estimation latency for the experiments is 55 seconds, which is well within the requirement of 1 minute. However, the experiments were limited to 50 modes max due to the simulation memory constraints. Similarly, the data collection latency is in seconds. Since it is not a real-time application, this is acceptable. The average position error that we get is 4 meters. RPE algorithm suffers from the problems of error accumulation and error propagation. In addition, RSSI method is not good for emergency situations because it requires real power measurements. In the end, we propose some future works for improvement mechanisms to avoid error accumulation, extensive experiments with more modes and more beacons, support more than one sync node, which will potentially require a new routing algorithm. And the last one, the power analysis of the introduced method. This will help evaluate the energy consumption and possibility of using duty cycle for better efficiency. This brings us to the end of the screencast. Thank you for watching and have a nice day. And don't forget to like and subscribe. Thank you.